All right, for the next set of topics this week, we're going to talk about bedforms and sedimentary structures. Again, I'm going to break this up into two lectures. The first one will talk about bedforms and the different processes or the different flow conditions that generate different types of bedforms. And then in the next lecture, we will talk about the types of structures that get created by bedforms and by other types of sedimentary processes. So to get us started off, bedforms is the term that is used to sort of encompass all manner of periodic topographic features that are formed by the transportation of sediment. Okay, so things like ripples and dunes and so forth. And the type of the form that we are referring to is going to be determined by the interaction of the fluid in the bed. So different fluid dynamic situations give rise to different types of bed forms that we'll discuss in this lecture. Okay, so for example, here's an image of an antidune here, where the water and bed are perfectly in phase, and we'll talk a little bit about each of these. Okay. Bedforms can be incredibly useful to stratigraphers as we go about trying to interpret past environments, because as migrating features on the landscape, they leave behind a record of their passing oftentimes. And so these bedforms can give us information about a number of things. One being the fact that because they form in currents, right, they can tell you the flow direction and potentially the flow strength. They also form in flows like oscillatory, in oscillatory flows like waves, right, where a wave is moving through a system, and so the velocity field goes both from the left to the right and then to the right to the left, leaving behind these symmetric ripples here. And so that can tell you something about the wave strength. And so these are really useful for sedimentologists and stratigraphers to look at, because they give us all sorts of information about what type of environment it was. Was it a unidirectional current environment, or was it a wave environment? And potentially something about the magnitude and direction of those forces, right? How fast the flow was moving, for example, what direction the flow was moving, and so forth. So those can be really handy and something that a lot of stratigraphers spend a lot of time working on, myself included. Okay. So we can start off with oscillatory bedforms. Oscillatory bedforms result from the periodic switching of direction of waves. In this case, you can see this is a flume where there is a piston, presumably somewhere, that is moving the water back and forth to simulate what a wave would do. And you can see that the forms themselves are built up by this sort of periodic motion of sediment over the crest from one direction to the other direction to the other direction, and so forth. Okay, so these are wave ripples. And in a purely oscillatory environment, the wave ripples might be or will be symmetric, right? So you see that the slope on both sides is approximately equivalent, and that's how you might interpret them in the field. But as you might know from being out in the ocean or being out at the beach, that waves can also be quite complicated, and so they can often leave behind really interesting records in different environments. For example, here's an image of a bunch of different wave generated oscillatory bedforms, and interactions between different kinds of flows and different types of sediments can result in really neat oscillatory bedform patterns like these, ladder back ripples here. These are called, to just standard, very, very beautifully linear oscillatory ripples, to much more complicated bedforms. They often bifurcate, like you see here, resulting from instabilities as they're forming. And so oscillatory bedforms can tell us a lot about the the fact that the wave action was the dominant transport mechanism. Once you get into a situation where you have even just a little bit of currents, it doesn't take much. The bed forms, even in an environment that has a lot of oscillatory motion, if there's some downstream component, the bed forms will very quickly change their shape to become asymmetric and steep on one end. That's been demonstrated in experiments. So the fact that you find a ripple that has symmetry on both sides of it, so both sides are the same steepness, tells you very, very conclusively that you are in a sort of an oscillatory wave-driven system. Okay, so we won't focus too much on oscillatory bed forms, other than to say that that they are symmetrical in form, and that's how you would interpret that they formed in a wave transporting environment. But we're going to focus primarily on unidirectional bed forms in the rest of this lecture here. And by unidirectional, I mean unidirectional current, right? And so in this case, we're referring to, say, a river, for example. This can also apply in tidal systems where you know, a flood tide versus an ebb tide might move more sediment in one direction than the other, right? And so in this case, we get a variety of different bed forms that can be created by those kinds of currents, and they generally tend to vary as a function of the flow strength, if you will, very roughly speaking. And the reason I say that is it's because it's different properties of the flow that result in the transition from one type of bed form to the next. And so we're going to talk about each of these in detail, but we start out with ripples, which are small scale features, and their patterns don't result in, say, boils or eddies that impact the water surface. We'll talk about dunes. Dunes result in large scale flow circulation and eddies on the fronts of these dunes, like you'll see here, and they shed a wake that does result in water surface topography. Dunes can be large features relative to the flow depth, up to, you know, a third of the flow depth or so. They can have superimposed ripples on the back of them. That's fairly common. And then as flow strength increases, they start to wash out. As suspension increases, dunes are primarily a bed load dominated bed form. As suspension increases, the dunes become washed out, and you get into a transition, and then into upper stage plain bed, it's called, where the bed is planar. This is a relatively, while unstable in much of the world's rivers, it does occur, and it is fairly common in some situations, in particular at the tops of sandy bars. As flow strength increases even more, you get into antidunes. In the big difference that you'll notice between antidunes and dunes is that with dunes, the water surface, the wake that is cast by the dune results in an upward deflection of the water surface above the trough at the front of the dune, so the water surface and bed surface are out of phase with each other. Whereas for an antidune, the antidune results in a much larger perturbation to the water surface, for one thing, and it's in phase with the bed topography. So the high points in the water are the high points in the bed, and that's the opposite for dunes. As flow strength increases even further, you end up with breaking waves over these antidunes. In all of these cases, by the way, flow is from left to right here, and the waves will break backwards or upstream on an antidune. And ultimately, those can sort of almost smear out, if you will, into these longer features called chutes and pools, or cyclic steps, they're often referred to, where there's a much longer sort of flat plain bed condition between the two breaking waves, if you will. Okay. So we'll talk about each of these as we go through, sort of in progression. The first one we'll start off with, which was not on that previous figure, is what's called lower plane bed. So below ripple stage, you get what's called a plane bed, where you just have very, very low amount of transport, not a lot of grains moving at a time, so you don't build up bed forms. Particles are not colliding enough to build up those sort of to allow those perturbations in topography to grow, if you will. So it occurs around about the threshold of motion, where this term T star, the transport stage, which is the ratio of the shear stress of the flow to the critical shear stress of the particles. So how much more is the shear stress than the critical amount required to move sediment? And when it's pretty close to 1, so less than 5, you often end up with lower plane bed, especially in coarse bedded materials, right? So it's more stable in gravel and coarser materials. Sand tends not to form lower plane bed, although it does happen. So here's some images of that. In a river, you can see it's a change in grain size in this particular location that results in the transition between ripples in this finer material and lower plane bed in this coarser material. This is the top of a bar that would have been inundated, say, in a previous flood condition, for example. You'll often see in cobble-bedded rivers where plane bed is common, that you get imbrication of the cobbles if they're in any sort of elongate form. If they're not, perfectly equant A, B, and C axes, you might get flat cobbles, and so you'll see that oftentimes you get imbrication where the cobbles on these flat surfaces align themselves with the flow. And you can actually use that to infer the flow direction if you see that in a stratigraphic deposit, right? So they become hydrodynamically more stable. If one of them rolls over and the next one rolls over on top, then the flow can move over top of them much more easily without re-entraining them. Okay. So then the next step that occurs as flow strength increases, or as particle size decreases, is ripples. Ripples tend to occur in a laminar flow sublayer, so where flow is not necessarily very turbulent. So if you have a relatively deep flow that is not moving very fast, you might not have a lot of turbulence that impinges directly on the bed, and so you end up with a layer towards the base of the bed that is predominantly driven by laminar flow. So the flow near the bed is not turbulent. In that case, you can get ripples. They're small. In this case, they may shed a small wake, but not that much. You won't necessarily get suspended sediment flying off the front of these ripples. But they will not tend to interact with water surface, right? So they'd be confined to the sort of lower sublayer of the flow, if that makes sense. Okay. They're generally small and do not interact with the water surface. They do migrate downstream as sediment is entrained or eroded off the back here, right, and then transported and deposited on the front of the ripple. So the material gets excavated from the back, deposited on the front, and these will migrate downstream. Okay. Here's some images of some ripples in a flume here. You can see that relative to the water depth, they're quite small. They may be only 1/10 or 1/15 of the total depth of this flow, and that's relatively common in rivers or in ripple beds. Okay. As you transition into a more turbulent regime where the turbulence is impinging on the bed, then you end up in a situation where you can build dunes. And in this case, these dunes will shed a wake, right? So you'll end up, just like with ripples, you get sediment entrained off the back and deposited on the front, but you end up with a flow separation eddy here that can form, and you also end up with a pressure gradient and a wake that occurs over these over these dunes, which results in a slight low over the crest itself as flow accelerates over the crest, and then a slight high as the wake sort of impinges and as you get flow deceleration over the trough of this dune. So we refer to the top of the dunes as the crest and the bottom of the dunes as the trough, right? And so you end up with a water surface that does interact with the dunes themselves, right? And this results in the surface waves being out of phase with the bed topography. So the lows in the water surface are over the highs in the bed. If you are interested in a complete derivation of why this is, there's a PowerPoint presentation here by I believe this one's by Gary Parker, who goes through the complete fluid dynamic derivation. You're welcome to click on that and view that. Okay. As to why the bed surface and the water surface are out of phase. It can be derived mathematically. And again, like ripples, these migrate downstream by the removal of sediment from the upstream side, which we call the lee side, and deposition on the stoss side. Opposite. Sorry. This is the stoss side here is the upstream side, and the lee side is the downstream side. Okay. And so what that looks like here is this is a video from a Flume experiment that I did for my dissertation. And you can see this is sped up, so it's a high-speed video. You can see the particles being entrained and moved as bedload off the backs of this dune here, and you can watch as they get deposited on the front, and you can see little avalanches occurring, right? So as the flow decelerates right here at the brink, you get a flow separation, and you get this turbulent eddy, and the particles can't fly any further past there, most of them, and so they get deposited right there at the brink, and you can watch the dune migrate downstream as a function of that, okay? These are among the most common bed features in sandy rivers worldwide. If you can't see them if you go out to the Mississippi River right now, but if you were to say go out on the river on a boat with a fish finder and go upstream, you could see the topography on the bottom of the river has dunes that are on the order of a couple to 5 meters tall, right? And those are dunes at the bottom of the Mississippi River. So most sandy rivers do have dunes. I could show you some imagery of those if anybody wants. So we use a lot of terminology when we refer to dunes, and this becomes important, especially in sedimentology and stratigraphy, because dunes result in the deposition of stratigraphy that is fairly common in the Earth's stratigraphic record, and indeed also other planets. There's dune stratigraphy on Mars. And so we think about dunes in a variety of different ways, but here's some terminology that might get used. So the crest here, like I mentioned, refers to the top of the dune. The trough refers to this low point in the dune, right? You might have the brink point here, which is the sort of location where flow separates from the crest into the trough here, right? And so sediment that makes it past there makes it over the brink of the dune, right? That's where most of the sediment stops moving and then sort of piles up until it reaches past the angle of repose and then avalanches down, okay? The front or the face of the dune, this avalanche face here, you'll often hear referred to as the avalanche face. That's the lee side, right, or the downwind side or the downflow side of the dune. And then this upflow side of the dune here, or the where sediment is being removed from, is called the stoss side, okay? And the wavelength or the length of a dune is from crest to crest or from trough to trough, depending on how you define it, depending on how you're measuring it. Okay, and so these are some common terms you'll hear kicked around, especially in the stratigraphic and sedimentologic universe. And we'll talk about these as well when we do our lab this week. Okay, so that's dunes. As flow speed increases, or as flow strength relative to depth in particular increase, you end up in a condition where the dunes will start to wash out, right? So the dunes are no longer stable because you don't have bed load moving as the dominant process. And so the bed load particles are no longer colliding to build up these topographic features that become dunes. You end up in a situation called upper stage plane bed or upper plane bed. In this case, the bed forms become washed out and the bed is relatively flat. And here's a video of this. It's not super stable. It's actually not very easy to get and keep in a Flume, but this is a Flume channel at the University of Minnesota. It's a video that I took, I guess, 3 summers ago now. Time flies. Of upper stage plane bed in a Flume, and you can see that there's relatively low water surface topography, although there's a lot of high frequency topography. That's the turbulent. It's a very highly turbulent condition. This is about, I think, 3 meters wide for scale. This is a really cool Flume, by the way. This is we're here down at the bottom of the Mississippi River. This lab is in the middle of the Mississippi River in Minneapolis at St. Anthony Falls, and this is Mississippi River water that gets plumbed through the whole building to run all of their flumes. And so this is actually the Mississippi River in a Flume in a lab here being shown here. So in this case, the water surface and the bed surface are going to be relatively flat. So as you can imagine, the stratigraphy that might get generated from this would be just planar laminations, right? And this occurs at a condition that we call critical Froude number conditions. And what that refers to is the sort of the conditions at which the downstream advective component of flow dominates over the potential component of the flow, which is sort of described by this term here, the Froude number, which is a relatively commonly used term, which is the ratio of the velocity of the flow to gravity times the depth of flow to the square root of this GH term, right? When Froude numbers are about 1, we refer to that as critical, and that is when you get this upper stage plane bed condition. So if you see plane bed flow out in the wild, you can impress your nerdy friends by saying, well, that's a Froude critical condition of Froude number of 1. It's a dimensionless number. You can see it has units of velocity here, right? Say that's meters per second, and this is meters per second squared times meters, so the square root, so it's meters per second divided by meters per second, right? And it's a dimensionless number. And that defines more or less the transition between subcritical flow, where bed forms occur, and supercritical flow, where things like antidunes start to occur. Okay. And so the next stage as you go up in Froude number or up in flow strength is antidunes. And in this case, right, so the antidunes are these features where the flow or the water surface is in phase with bed topography, right? High points in the flow are over high points in topography. And unlike dunes, antidunes actually migrate upstream. So it's sediment that is, so if the flow, I can't quite tell in this image, I can't remember if the flow is moving left to right or right to left, but it looks like it's moving from right to left in this case, and you can sort of see that there's some stratigraphy being formed here, these cross beds. And it's, even though the flow is moving this way, the topography is actually going to be moving in this direction because it's sort of driven by scour on this side and deposition on the upstream side. Okay, and so those are kind of interesting, and you end up with very interesting stratigraphy that gets formed by those. And again, those are Froude numbers of greater than 1, right? So as you pass that critical stage and into what's called supercritical Froude number conditions, that's how you get antidunes. And here's a video of that from the same Flume experiment in Minnesota as the previous video. You can see, if you watch them closely enough, maybe you put your mouse clicker, well, okay, that didn't quite work because I started scrolling. You can see that if you follow one wave in particular, it starts to migrate upstream. So this one's at this sort of like little line in the tank here, and it's moving upstream. Flow is coming from the upper left to the lower right in this case. And if you saw that particular standing wave here, which is over a dune, an anti-dune at this point, right? At this point in time, it's right over this line, and then as I scroll down, you can see it's moving upstream. You can see the standing wave is migrating upriver in phase with the bed topography. So the anti-dune, the actual topography is also migrating upriver, right? So can you see that? And these give way ultimately to breaking waves and cyclic steps, right? So as Froude number becomes much higher, you end up with a breaking wave separating hydraulic jumps, right? And this is not super common in sediment transporting environments, but it does occur where you end up with a breaking wave over the bed, right? So this is the bed topography here. This is the water surface. You end up with a breaking wave at the front. It breaks upstream, right? So the wave breaks backwards, if you will, upstream. And those get separated by a subcritical component of the flow where Froude number is low, and then the Froude number, it increases, and it increases to much greater than 1 here at the hydraulic jump, right? So Froude number would be 1 about here, and it might be 1.5 to 2 or more here, okay? And these migrate upstream as well, but they're longer and lower amplitude than antidunes would be, okay? They're not super common, and they do migrate upstream, but here's an example of what they might look like, and I'll show you a video of this in a second. So these are cyclic steps where you can see these are chutes and jumps, right? So each of these is where this is the breaking wave, are the jumps here, right? The flow is moving in this case from right to left. This is Great Sand Dunes National Park here. And so here the flow is subcritical, here the flow reaches critical, and then right at the jump it's supercritical, okay? So they're relatively uncommon. Here's a video of them happening. So this first thing here, this is a roll wave, which is a big aggregation of supercritical shock wave conditions, which are really cool. Then you can see you get standing waves and antidunes starting to form, and then they transition as the flow gets thinner, right? But the velocity stays high into these cyclic steps. So as you can imagine, right, the Froude number is increasing through this transition, through this progression. Another one's going to come here. So here's another shock wave or roll wave, right? You get upper stage plain bed right behind it. Then you get antidunes, and then the flow is getting thinner and thinner and thinner, and so you get higher and higher Froude numbers, and so you transition through the whole range of critical bed forms here. It's a pretty cool place, and this happens, it just repeats itself on a 25-second increment here. And we can plot all of these transitions into the space, into the phase space that allows us to predict when a particular bed form might become common. And we do this in what are called phase diagrams, and these can get actually quite complicated. But the reason we do this is because we, as stratigraphers, might see the deposits of one particular type of bed form in the rock record, and we might be interested in understanding what the flow velocity was given that particular grain size that was left behind and that particular bed form that was left behind. And that might tell us something about the flow speed or the fluid dynamic conditions of that river in the past, which is actually really useful for us to know as stratigraphers. Okay, and so we use these things. They're very common. They're called phase diagrams. Here's an example of one. It is by no means the only one, and they all have different ways of defining the axes, and these get complicated because they're a function of grain size, flow depth, and flow velocity, so they're sort of multi-dimensional in this case. So you can see that this has flow velocity and grain size on this axis, but it's a slice through a three-dimensional space for a particular set of flow depths here. And you can use these to sort of compartmentalize where different bed forms might become stable. You can see the Froude numbers here are listed, right? And so if you were to say go out into the field, you might be able to say, oh, I see a dune deposited here. And actually it's a two-dimensional dune, which is to say one that doesn't have much variation in the cross-stream dimension, right? And you might say, okay, well, that's going to fall somewhere in this phase space. And I think from other information that I saw that the flow depths were around 0.5 meter, or say it's 0.4 meters since we're on that slice here. Okay, well, I think we're probably in a flow velocity of somewhere between 0.4 and 0.7 meters per second, right? So it allows you to sort of make that first pass estimate of where in the flow velocity space you might have, your flow might have existed. So you can imagine where that might be useful. But again, the reality is that these phase spaces are much more complicated than that. And again, they're a function of both the velocity, the depth, and the grain size here. And so it's actually a three-dimensional space, and there are much more complicated versions of this that are a little bit more, I would argue, physically based and more accurate, but these are common to use where you can plot for various different, you can pick if you're interested in depth and grain size, but you know the velocity, then you can take a slice in this dimension, or if you have the depth and velocity and are interested in the grain size, you can take a slice in this dimension, right? Or as we saw in the previous slide, if you have grain size and you're interested in velocity, but you know the depth, then you can take a slice in this dimension. Does that make sense to everybody? And so those can be useful in a number of different situations, and a lot of people continue to work on actually refining these phase diagrams to be a more precise tool so that you can actually put yourself in much more confined places on there and actually know a little bit better what your flow velocity was or your shear stress was or something like that based on the shapes and sizes of your dunes, okay? Or of your bed forms, I should say. So that sort of wraps it up as the lightning round of bed forms. And we're going to move next into the lecture where we talk about sedimentary structures and what kind of structures get left behind by different forms on the bed. And so I'll post that after this. Thanks.